Hi, I'm Hanson Lee doing the AP Physics 1 second semester FRQ 1. Let me get straight into it. So, A section for the force body diagram. Let me draw that real quick. Hope you can kind of see that like clearer. But there's gonna be three forces. So the shortest force is gonna be Fk. Shoot, that's how. Hi, my name is Hanson Lee. I'm doing AP Physics 1 second semester FRQ 1. Okay, let's go straight into it. A is asking for the force body diagram. So let me draw that real quick. So like this dark line is the ramp, and then this is the hoop. So for the first force, let me just make it like lighter. You can still see that. You can. The first force I'll be doing is Fk, which will be where the hoop touches the ramp, and then it'll go up the ramp to oppose the motion. It's also like Fs, but because it's rolling without slipping. But this will be basically the shortest one. And then Fn will be also coming from the same point because it's the contact force from touching the ramp, so be going in this direction. And Fg will be the longest force I will draw, and it will be going from the center of mass and then goes straight down because that's how gravity works. So I drew Fk the shortest because it's Fk is basically mu Fn and mu s or k in this case, and so mu is never like anything like 1 or greater. It's usually like point something, so that means it has to be less than Fn, which is why it's shorter. And Fn is like Fg cosine theta if you draw out the components. So because it would be Fg y, which would be Fg cosine theta, and cosine theta like at an angle it would be point something, so it would also be less than Fg. So Fg the longest, Fn's the second longest, and then Fk. Okay, B is asking for the linear velocity. I'm gonna do mechanical energy. So first off, you're gonna have PE G, like the potential energy from gravity, and KE rotational plus KE lin. The reason why I didn't add PEG for like at the end is because because I'm measuring the height from the top of the ramp to the bottom of the ramp, which is like the tabletop. So if I did include it, it would just cancel out. So I'm just not going to include it because I'm just setting that as the height, like the bottom of the ramp as the height. So this would be m naught g lowercase h naught equals 1/2, and this would be I lower subscript h omega squared plus 1/2 m naught v cm squared. So we want to find v. We can change this into like the same terms here. by doing this. So the inertia for a hoop is 1 mr squared. So basically 1 is the same thing as it's invisible, and then r naught squared, and omega is the same thing as v over r, so this becomes VCM over r naught, and since it's squared you can just like distribute the square to like the entire fraction, plus 1/2 m naught VCM squared. This becomes m naught g h naught equals 1/2 m naught, and r naught squared cancels out, so it'd be VCM squared plus 1/2 m naught VCM squared, which means that you can, since they're the same terms, you can add these together. So 1/2 plus 1/2 is 1, so just be m naught VCM squared. You can cancel out the m naught on both sides, and then square root both sides, which would be VCM equals square root g lowercase h naught. So square root g lowercase h naught. Yeah. Okay. C, I'll do it here. C is asking for ratio of k rot to k total. So we found what k rot is like converted to m naught and VCM. So it's basically 1/2 m naught VCM squared, and k total we also like found because we ended up adding the ke rot and ke lin, which is how you find the k total. So which was I kind of like crossed it out, but it was basically m naught VCM squared. The square root, we just did that to find v. You can add a 1, it doesn't matter. So it's asking for the ratio of rotational over total, so 1/2 m naught VCM squared over 1 m naught VCM squared. These cancel out, so it's just 1/2 over 1, which is basically just 1/2. So 1 ke rot to 2 ke total. Let's do D. D's asking, the student claims that the linear acceleration is constant. So ACM is going to be equal to g sine theta over 1 plus c for an object going down a ramp that rolls without slipping. But keep in mind that the ramp is curved, so theta is always changing. So I disagree, because ACM changes as theta changes along the curved ramp. So disagree. So it's not constant. I'm gonna be doing E here. E, so if the height of the ramp is doubled to 2 lowercase h naught, and the linear speed at the bottom of the ramp will also double. So we found it in this equation, so we can just plug it in. Obviously you can tell that the 2 is inside a square root, so it's not going to be VCM will not be double. So disagree, because VCM will not double but multiply by square root of 2, which is basically like 1.4, I think. I'm pretty sure, yeah. F. Okay, so now the hoop is gonna leave the table, and we have to find the time of flight once the hoop leaves the table. So I'm gonna use this displacement formula, equals VIXT plus 1/2 AXT squared. Keep in mind that when the hoop leaves the table, it's gonna go like straight this way, which means all VCM becomes VIX, and there's not gonna be any VIY. So you can put VCM for here, and also keep in mind that VIX, there's no acceleration, so like in free fall, so VIX doesn't change, so there's no A in free fall. So the displacement is the same thing. The horizontal displacement from the table is the same thing, and it's given as D. And remember that VIX is just going to be V because it leaves the table horizontally, so it's going to be G H, like lowercase h naught, times T. So you can just to find T, divided by square root G lowercase h naught. So T equals D over square root lowercase G lowercase h naught. If you want, you can rationalize it. So let me do that real quickly. Okay, you can still see it. Nice. Shoot. Okay, so T is basically all that. T equals D square root G lowercase h naught over G lowercase h naught. Okay, now G is asking for the horizontal distance, but in terms of lowercase h naught and uppercase h naught. So basically, we want to get rid of this T. So I'm actually going to be using this part because it's just like cleaner. And we can find T using uppercase h naught by doing this. You can use the vertical displacement. So remember that it becomes all VIX, so there's going to be no VIY. And the vertical displacement that will fall is just going to be equal to uppercase h naught, like the same magnitude. And the vertical acceleration is going to be just G and then T squared. So we're going to be solving for T, so then we can substitute it back in. So times 2 both sides, divided by G both sides. So it become 2 uppercase h naught over G equals T squared. So square root both sides. So T equals square root of 2 uppercase h naught over G. And then we can plug it back into here. So D equals square root G lowercase h naught times square root 2 uppercase h naught over G. So this becomes, when you multiply a square root, it's just like square root of everything multiplied together. So D equals square root G lowercase h naught times 2 uppercase h naught over G. So, and the G's cancel out. So D equals square root 2 lowercase h naught uppercase h naught is our new horizontal distance using only lowercase h naught and uppercase h naught. Okay, H. Student claims that the English speed will increase after it leaves the table because of the net torque acting on the hoop during flight. So the thing that's wrong with that statement is the only force as the hoop leaves the table, the only force acting on it would be F of G because of gravity. So, and it says that this force, the only force, should be producing a net torque, but Fg touches the center of mass, which means that it would have no R, because R is the distance from the axis of rotation, but it's touching it. So disagree, because only force, gravity, produces no torque as it touches center of mass / axis of rotation. Okay, I'm gonna flip to the other side. Okay, there, can you see that? Take a few seconds to read it. Okay. Now the paragraph. Okay, for I, we're doing the same situation, but now the hoop is a solid disc with the same mass and radius, but with the moment of inertia of I of d. So we have to see what this changes. So the biggest thing it's going to change is this part right here, and let me show you why as I do it. I'll be writing the paragraph after I show you my work. So everything's going to be the same. It's going to be still PE G. Let me show you all my part. So PE G equals KE rotational plus KE linear, which would be M naught G H lowercase h naught equal 1/2 I, but now ID, so this is changing, omega squared plus 1/2 M naught VCM squared. So now I of D is different, and the moment of inertia for a solid disk is 1/2 M squared. And everything else will remain the same. So remember, distribute the square to the entire fraction. So now we have this side equal to 1/4 M naught VCM squared plus 1/2 M naught VCM squared, which means we can add these, but now the fraction will be different, as this has a denominator of 4, so we have to change this to 2/4, which is going to be equal to 3/4 M naught VCM squared. Cancel these out, times 4/3 to get rid of the 3/4, so 4/3 G H naught equals VCM squared, square root both sides. So VCM is now square root 4/3 G lowercase h naught, which is different from what we got over here, which is square root G lowercase h naught, and this one has a 4/3. Okay, so by changing this, we changed this, because remember that we used VCM for VIX, but also keep in mind that what we did in G doesn't change. So how we found T doesn't change, because we didn't use V at all. We just crossed out VIY, and everything else in G should remain the same, like uppercase H naught, G 1/2. So we can do this formula as it leaves the table and replace this VIX with all of this. So remember, this is the distance equals, now it's square root 4/3 g lowercase h naught times time, and remember there's no acceleration for VIX in free fall, so we can just cross that out, and d equals square root 4/3. And remember what I said like 2 seconds ago, everything we did for t wouldn't change as the hoop is replaced with the solid disk. So we can just put, for t, we can just put square root 2 uppercase h naught over g again. So now our distance is multiply the square root so everything's together. So 8g lowercase h naught over 3g, oh yeah, and uppercase h naught on top. And the g's cancel out, so d equals square root 8 over 3 lowercase h naught uppercase h naught. So in total, our horizontal distance 2 is less than 8 over 3, because you know that 2 is already equal to 6 over 3, and 8 over 3 is more than that. So the distance for the solid disk will be greater. And let me just write down like what I'm gonna say. So can you see it? Okay. In total, the solid disk will have the greater horizontal distance, although the mass and radius stay the same, because it's asking like compare them. Although the mass and the radius stay the same, they do not matter in calculating the speed at the bottom. And because here r naught just canceled out, so we didn't even care about r at all, and m naught canceled out. So even though the mass and the radius stay the same, they do not matter in calculating speed. Instead, the inertia's coefficient changed the speed. So the inertia's coefficient changed the speed because the coefficient of a hoop is different than the solid disk. And the reason why the coefficient changed was because having the same mechanical energy at the start, the solid disk turned less of it to rotational kinetic energy because its coefficient was less, 1/2. See? So this meant that our K rotational was only 1/4, which meant that more energy could go to K linear. Thus, allowing for more energy to become KE linear and raised the final speed at the bottom of the ramp with more speed the solid disk traveled a farther horizontal distance, as you can see by d equals like VIX times c, VIX being the greater VCM that we found here. So yeah, that's it.